Hi, in this video we are going to discuss about poles and zeros of LTI filter, and we'll look at the geometric interpretation of this. Okay, so what are poles and zeros? So let HZ equal to this form. Basically it has got poles and zeros in the numerator and denominator. A is some magnitude and our xi k are the zeros and lambda k are the poles. Right, this is the general form where we have written our h of z, which is the transfer function of an LTI system in terms of these factors. Now then h e to the power j omega. So what you do to get e to the power j omega? You remember that z is a general complex number and e to the power j omega lies on that unit circle, and it's simple, just replace z with e to the power j omega in the above equation and the same thing. Now one thing you notice that I have taken, instead of z inverse I took the z here on the before the negative sign, like the z inverse, it went here and then I took z inverse common, and because of that this extra term appeared, and the order of this term will be equal to n minus m, right? So okay, now what is the magnitude response? I got my h to the power j omega. What is the magnitude response? It is simply the amplitude or the mod of h to the power j omega, and this is equal to mod of a into mod of individual terms. Now what is the phase response? The phase response is angle of h to the power j omega, and how do we find it from our factors? So if it's basically if a is if a is a complex number, then you take the argument of a plus omega times, remember this term, omega times n minus m, right? Because these are phase, so you have to look at the overall angle of this complex number. This is a complex number. What is the angle? So all the angles get added and subtracted accordingly. So you got omega n minus m term from here, plus the phase of this term, which means k equal to 1 to capital M, argument of this term only, e to the power j omega minus gamma k, minus the argument of these terms, and you are seeing that how multiplication becomes addition or subtraction. So you take argument of the poles, the denominator factors. Okay, so this is the general form, and we can see the magnitude and phase response. Now let's look at the geometrical interpretation of the whole thing. So let's look at the magnitude response first. Let us take a simple pole zero plot where we have a zero somewhere here. It is 0.8 times the angle is 60 degrees here. So this is my zero. Let us call it as zeta 1 and 0.8 e to the power minus j pi by 3. Now my term, like the h e to the power j omega, will be e to the power j omega minus this zeta 1, right? So let's consider this term. So let us imagine there is some hypothetical h e to the power j omega, which is this. What is the magnitude of this term? Now remember that omega is varying over this circle. It goes from 0 to pi, and similarly 0 to minus pi, basically minus pi to plus pi. So we have to find this value, how it changes when it goes from here to here, right? So basically, if you see, this is my e to the power j omega, where this angle is omega, and what is this term? This term is this distance, And if you are here, the distance is this much. If angle is increasing, the distance becomes very small. It becomes 0.2 here, right? The whole length is 1. This is 0.8. This is 0.2 here, the smallest value at omega equal to pi by 3, right? And then you go further, then this length will again start increasing. So this is equal to my length of this vector, which I have plotted with dark here. This is my vector. So let's try to plot it in the magnitude plot. So what is my magnitude, this term? So as I'm changing my omega, you see around 0 the magnitude is large, and then it becomes very, very small, and then again it increases, right? So this is around pi by 3. So around 0 my magnitude is large, then it becomes small, then it again becomes large, and it becomes very large here, and around here it will be the largest distance. How much will that be? That will be 1 plus 0.8, 1.8. That is the largest value, and smallest is 0.2. So around pi by 3 it is 0.2, and then around pi by 3 plus pi, it will be around 1.8. Okay, so basically this is how it looks like. Now let's look at the phase response of this term now. So our term is there, that e to the power j omega minus zeta 1, which is 0.8, that thing. Now what is the angle? So geometrically the angle is basically this angle, right? This is a vector, right? This is a vector, and the angle of this vector, argument of this vector, is the angle with respect to the z-axis, or x-axis, the positive x-axis, right? So this angle is this theta. So this angle is equal to theta, and it is a function of omega. That's why you can write it as theta omega also. Theta is a function of omega. Let's plot it now, how it looks like. So on the y-axis I have this theta as a function of omega, and on the x-axis I have omega. Now my angle will be, if it is here, it's a negative angle, right? If I'm at 0, it is a negative angle, and as I'm increasing my omega, theta is decreasing. Here it becomes 0, almost 0, right? Here, when what is this point? This is the point when the x component of both of these are same, right? Which means my omega, basically, the sine of omega is equal to the sine of this term, sine of pi by 3, right? So it becomes 0 somewhere here, and then it is increasing, and until it reaches pi, it will be more, and it is symmetric. No, it is not symmetric. So if you go in the negative direction, it will decrease, and when it reaches here, it is large negative value. It decreases here, so it is not symmetric. So okay, and at pi by 3, the angle will be, how much will that be? At pi by 3, the angle will be pi by 3, right? This angle will be pi by 3. Omega and theta will be same here. Similar angles. Okay, so anyways, let's complete this plot. Let's use my program to do this whole plotting. This is my h of z, which is z minus 0.8 j pi by 3. Why did I write a minus sign here? It should be a plus sign here. I'm sorry. It should be a plus sign here, not a minus sign. Okay, so we have this is my h of z. This is the correct one. Now I have this part, which is the magnitude response. You remember that this is what we got around pi by 3. The magnitude was very small, 0.2, and then it increases. increases. And now what does the phase plot look like? See, it is at 0 it is negative, and somewhere here it becomes 0 and it increases. And here, why does it make a jump? Because of modulus, right? I want my angle to lie between plus pi to minus pi to plus pi. Therefore, as soon as it crosses plus pi, you deduct that part, the modulo 2 pi basically. Okay, so but actually it can keep increasing if you do unwrapping. Okay, now this was my one example where h of z looks like this. Let's take another example. Okay, let's look at another example. This is h e to the power j omega is simply e to the power j omega, right? What does this mean? It means that it has no zero, no what do you say? No zero, no. I don't know. You can say it has a 0 at 0. Yeah, I'm sorry. It has a 0 at 0. Basically, if I look at h of z will be 0 when z is 0, right? Because h of z is equal to z. So I have a 0 at 0. Okay, now let us look at the phase plot and the magnitude plot. So first the magnitude plot. So it's got j omega magnitude. This is equal to how much? 1. This is simply 1, which means it is a constant for all omega. Now let's look at the phase term. The phase of h to the power j omega. This is equal to omega. That's it. So this is the simplest function probably to plot. Let's plot it. So it's very simple. It is simply this is what my h e to the power j omega looks like, right? It is always 1 for all values of omega. And now what about the angle? Angle is just constant. I mean the linear. So my y is equal to x. Yeah, so this was another example. Now if I do the programmatically, I plot it, and that's what I get as expected. Now let's look at another example which is a little different. Here we have z minus 0.2. Now here my 0 is at 0.2. Okay, it's quite similar to the first example actually we saw, but let me do it so that you can get an idea. So this is how it is, that my 0 is here, and my e to the power j omega moves about this circle. Basically starts from minus pi, goes all the way up to plus pi. Now let's look at the magnitude plot. The magnitude plot is simply here your distance is 0.8. Let me draw it. Yeah, and then as you go here, the distance becomes 1.2. That's it. Now let's look at the phase plot. The phase plot looks something like this. You have at 0, when omega is 0, your phase is also 0. And when your omega becomes plus pi, the phase becomes plus pi. When omega becomes minus pi, the phase becomes minus pi. But there's a catch, that this mapping is not linear. Because here, when you're here, that it moves very quickly. Like as your omega is moving, the rate of change of theta will be much larger than the rate of change of omega. So your slope will be more than 1. D theta upon d omega will be more than 1 in the beginning, and then it will be less than 1 later. So that's what you get here. Let's take the value plus pi. At plus pi, the value is plus pi, and 0, the value is 0. So, but the slope is more than 1 in the beginning and less than 1 later. That's what you get. And similarly in the negative part, it's just a mirror image of this. This is symmetric. So this is how you can plot. But now if we look at the real simulations, then same trend we get, same curve, and here same curve. It has got a slight curve here. Okay, now let's take another example. Now this time we don't work with zeros, but we work with poles. Let's first plot the pole zero diagram. This is my real part of Z, imaginary part of Z, and this is my unit circle. And then I got my point 0.2, but this is a pole here, not a 0 this time. So what I get here is, as I increase my omega, my distance is 0.8 in the beginning, and then it becomes 0.2. But since this is in the denominator, so the whole thing is reversed. These are just the plots. Now, so we are here. We have this. This is a pole, and then h to the power j omega is simply 1 upon this thing, the magnitude thing. But the okay, let's make the points here. So when my omega is 0, the value is when it is 0, the distance is 0.8, and so this term is 1 upon 0.8. And when when my omega is plus pi, then this term is this denominator, this distance is 1.2. Therefore, this term becomes 1 upon 1.2, right, which is smaller than 0.8. That's why I get this kind of hill-shaped curve here. And then what about the angle? Now, notice here that the angle of h to the power j omega is the negative of the angle of this line. My h to the power j omega angle is negative of theta, minus theta. So be careful here. So let's plot the endpoints first. My one endpoint is okay at 0, it is 0. That makes good sense. At plus pi, theta is pi. When my omega is pi, theta is pi, but I want minus theta. But minus theta, so minus theta will be minus pi. So I will get a point here. Similarly, when I go to negative pi, my theta is also minus pi, but minus theta will be equal to plus pi. That's why I get here plus pi. Now to join them together with the same idea that the slope, in the beginning the rate of change is large, and then later it becomes small. So around 0 the rate of change will be large. So it will be steeper here. And that's what you get. It is steeper here, and then it is steeper here, and that's what you get. Now let's, this is my geometrically drawn plot, but if we look at the simulations, they exactly match, right? So this is how we draw magnitude and phase response geometrically by looking at the pole zero diagram. And if you have multiple poles and zeros, then this term will be basically the magnitude plot will be the product of those lengths, and the phase plot will be simply the summation, right, as we had shown in general in the first slide. Okay, let's summarize the whole thing. So poles and zeros that are close to unit circle, they will bring about rapid changes in magnitude and phase, right? And as my poles and zeros are farther from the unit circle, the change which they bring about will be smaller, right? Why? Because we are measuring the length of the vector from the unit circle, because e to the power j omega always lies in the unit circle. So if that length is small, then 1 upon that becomes large, and then so that's why it brings rapid changes if my poles and zeros are close to unit circle. And in general, zeros, they cause a dip in magnitude, because that is the meaning of 0, right? The magnitude will go to 0 around those points. And the poles will bring peaks in magnitude. Basically, if you want to boost certain frequencies, you put a pole somewhere near that unit circle, inside the circle, for stability purpose, or so that DTFT exists. So for stability, you keep the poles inside the unit circle, and then the zeros are used to suppress certain frequencies. So wherever you want to suppress some frequencies, around those you put a 0. And then the poles and zeros which are close to each other, they cancel out when seen from far. But when you are near the poles and zeros, then they are visible. The effect is visible, but from far they're not visible. So basically, when e to the power j omega is far from two nearby poles and zeros, then you can just ignore the effect of those poles and the pair of pole and 0. And if it is close to the pair, then you have to still consider it. Yeah, thank you very much.